Leachate Treatment from Dr. Chandrakant Sawant. The leachate is any liquid that, in the course of passing through matter, extracts soluble or suspended solids, or any other component of the material through which it has passed. Leachate is a widely used term in the environmental sciences where it has the specific meaning of a liquid that has dissolved or entrained environmentally harmful substances that may then enter the environment. It is most commonly used in the context of landfilling of putrescible or industrial waste. In the narrow environmental context, leachate is therefore any liquid material that drains from land or stockpiled material and contains significantly elevated concentrations of undesirable material derived from the material that it has passed through. Leachate from a landfill varies widely in composition depending on the age of the landfill and the type of waste that it contains. It usually contains both dissolved and suspended material. The generation of leachate is caused principally by precipitation percolating through waste deposited in the landfill. Once in contact with decomposing solid waste, the percolating water becomes contaminated, and if it then flows out of the waste material it is termed leachate. Additional leachate volume is produced during this decomposition of carbonaceous material, producing a wide range of other materials including methane, carbon dioxide and complex mixture of organic acids, aldehydes, alcohols and simple sugars. The risks of leachate generation can be mitigated by properly designed and engineered landfill sites, such as those that are constructed on geologically impermeable materials or sites that use impermeable liners made of geomembranes or engineered clay. The use of linings is now mandatory within the United States, Australia and the European Union except where the waste is deemed inert. In addition, most toxic and difficult materials are now specifically excluded from landfilling. However, despite much stricter statutory controls, leachates from modern sites are often found to contain a range of contaminants stemming from illegal activity or legally discarded household and domestic products. When water percolates through waste, it promotes and assists the process of decomposition by bacteria and fungi. These processes in turn release byproducts of decomposition and rapidly use up any available oxygen, creating an anoxic environment. In actively decomposing waste, the temperature rises and the pH falls rapidly, with the result that many metal ions that are relatively insoluble at neutral pH become dissolved in the developing leachate. The decomposition processes themselves release more water, which adds to the volume of leachate. Leachate also reacts with materials that are not prone to decomposition themselves, such as fire ash, cement-based building materials and gypsum-based materials, changing the chemical composition. In sites with large volumes of building waste, especially those containing gypsum plaster, the reaction of leachate with the gypsum can generate large volumes of hydrogen sulfide, which may be released in the leachate and may also form a large component of the landfill gas. In a landfill that receives a mixture of municipal, commercial, and mixed industrial waste but excludes significant amounts of concentrated chemical waste, landfill leachate may be characterized as a water-based solution of four groups of contaminants: dissolved organic matter, alcohols, acids, aldehydes, short-chain sugars, etc. Inorganic macrocomponents common cations and anions including sulfate, chloride, iron, aluminium, zinc and ammonia. Heavy metals Pb, Ni, cubic, Hg and xenobiotic organic compounds such as halogenated organics, PCBs, dioxins, etc. For the physical appearance of leachate when it emerges from a typical landfill site is a strongly odored black, yellow, or orange-colored, cloudy liquid. The smell is acidic and offensive and may be very pervasive because of hydrogen, nitrogen, and sulfur-rich organic species such as mercaptans. In older landfills and those with no membrane between the waste and the underlying geology, leachate is free to leave the waste and flow directly into the groundwater. In such cases, high concentrations of leachate are often found in nearby springs and flushes. As leachate first emerges, it can be black in color, anoxic, and possibly effervescent, with dissolved and entrained gases. As it becomes oxygenated, it tends to turn brown or yellow because of the presence of iron salts in solution and in suspension. It also quickly develops a bacterial flora, often comprising substantial growths of sphaeroteluznatans. The primary criterion for design of the leachate system is that all leachate be collected and removed from the landfill at a rate sufficient to prevent an unacceptable hydraulic head occurring at any point over the lining system. There are many components to a collection system, including pumps, manholes, discharge lines, and liquid level monitors. However, there are four main components which govern the overall efficiency of the system. These four elements are liners, filters, pumps, and sumps. Liners, natural and synthetic liners, may be utilized as both a collection device and as a means for isolating leachate within the film to protect the soil and groundwater below. The chief concern is the ability of the liner to maintain integrity and impermeability over the life of the landfill. Subsurface water monitoring, leachate collection, and clay liners are commonly included in the design and construction of a waste landfill. There are several types of liners used in leachate control and collection. These types include geomembranes, geosynthetic clay liners, geotextiles, geogrids, geonets, and geocomposites. Each style of liner has specific uses and abilities. Geomembranes are used to provide a barrier between mobile polluting substances released from wastes and the groundwater. In the closing of landfills, geomembranes are used to provide a low permeability cover barrier to prevent the intrusion of rainwater. Geosynthetic clay liners (GCLs) are fabricated by distributing sodium bentonite in a uniform thickness between woven and non-woven geotextiles. Sodium bentonite has a low permeability, which makes GCLs a suitable alternative to clay liners in a composite liner system. Leachate drainage system. The leachate drainage system is responsible for the collection and transport of the leachate collected inside the liner. The pipe dimensions, type, and layout must all be planned with the weight and pressure of waste and transport vehicles in mind. The pipes are located on the floor of the cell. Above the network lies an enormous amount of weight and pressure. The collection pipe network of a leachate collection system drains, collects, and transports leachate through the drainage layer to a collection sump where it is removed for treatment or disposal. The pipes also serve as drains within the drainage layer to minimize the mounting of leachate in the layer. These pipes are designed with cuts that are inclined to 120 degrees, preventing entry of solid particles. Filters. The filter layer is used above the drainage layer in leachate collection. There are two types of filters typically used in engineering practices: granular and geotextile. Granular filters consist of one or more soil layers or multiple layers having a coarser gradation in the direction of the seepage than the soil to be protected. Sumps. For leachate. Well, as liquid enters the landfill cell, it moves down the filter, passes through the pipe network, and rests in the sump. As collection systems are planned, the number, location, and size of the sumps are vital to an efficient operation. Membrane and collection for treatment. More modern landfills in the developed world have some form of membrane separating the waste from the surrounding ground. and in such sites there is often a leachate collection series of pipes laid on the membrane to convey the leachate to a collection or treatment location. All membranes are porous to a limited extent so that, over time, low volumes of leachate will cross the membrane. Re-injection into landfill. One method of leachate management that was more common in uncontained sites was leachate recirculation, in which leachate was collected and re-injected into the waste mass. This process greatly accelerated decomposition and therefore gas production and had the impact of converting some leachate volume into landfill gas and reducing the overall volume of leachate for disposal. However, it also tended to increase substantially the concentrations of contaminant materials, making it a more difficult waste to treat. Treatment. Leachate processing/equalization tanks used in leachate treatment before releasing to a river. The most common method of handling collected leachate is on-site treatment. When treating leachate on-site, the leachate is pumped from the sump into the treatment tanks. The leachate may then be mixed with chemical reagents to modify the pH and to coagulate and settle solids and to reduce the concentration of hazardous matter. Traditional treatment involved a modified form of activated sludge to substantially reduce the dissolved organic content. Nutrient imbalance can cause difficulties in maintaining an effective biological treatment stage. The treated liquor is rarely of sufficient quality to be released to the environment and may be tankered or piped to a local sewage treatment facility. The decision depends on the age of the landfill and on the limit of water quality that must be achieved after treatment. With high conductivity, leachate is hard to treat with biological treatment or chemical treatment. Treatment with reverse osmosis is also limited, resulting in low recoveries and fouling of the RO membranes. Reverse osmosis applicability is limited by conductivity, organics, and scaling inorganic elements such as CaSO4, Si, and Bob. Removal to sewer system. In some older landfills, leachate was directed to the sewers, but this can cause a number of problems. Toxic metals from leachate passing through the sewage treatment plant concentrate in the sewage sludge, making it difficult or dangerous to dispose of the sludge without incurring risk to the environment. In Europe, regulations and controls have improved in recent decades, and toxic wastes are now no longer permitted to be disposed of in the municipal solid waste landfills, and in most developed countries the metals problem has diminished. Paradoxically, however, as sewage treatment plant discharges are being improved throughout Europe and many other countries, the plant operators are finding that leachates are difficult waste streams to treat. This is because leachates contain very high ammoniacal nitrogen concentrations, are usually very acidic, are often anoxic and, if received in large volumes relative to the incoming sewage flow, lack the phosphorus needed to prevent nutrient starvation for the biological communities that perform the sewage treatment processes. The result is that leachates are a difficult to treat waste stream. However, within aging municipal solid waste landfills, this may not be a problem as the pH returns close to neutral after the initial stage of acidogenic leachate decomposition. Many sewer undertakers limit maximum ammoniacal nitrogen concentration in their sewers to 250 mg/L to protect sewer maintenance workers, as the WHO's maximum occupational safety limit would be exceeded at above pH 9 to 10, which is often the highest pH allowed in sewer discharges. Many older leachate streams also contained a variety of synthetic organic species and their decomposition products, some of which had the potential to be acutely damaging to the environment. The risks from waste leachate are due to its high organic contaminant concentrations and high concentration of ammonia. Pathogenic microorganisms that might be present in it are often cited as the most important, but pathogenic organism counts reduce rapidly with time in the landfill, so this only applies to the freshest leachate. Toxic substances may, however, be present in variable concentrations, and their presence is related to the nature of the waste deposited. Most landfills containing organic material will produce methane, some of which dissolves in the leachate. This could, in theory, be released in poorly ventilated areas in the treatment plant. All plants in Europe must now be assessed under the EU ATEX directive and zoned where explosion risks are identified to prevent future accidents. The most important requirement is the prevention of the discharge of dissolved methane from untreated leachate into public sewers, and most sewage treatment authorities limit the permissible discharge concentration of dissolved methane to 0.14 mg/liters, or 1/10 of the lower explosive limit. This entails methane stripping from the leachate. The greatest environmental risks occur in the discharges from older sites constructed before modern engineering standards became mandatory, and also from sites in the developing world where modern standards have not been applied. There are also substantial risks from illegal sites and ad hoc sites used by organizations outside the law to dispose of waste materials. Leachate streams running directly into the aquatic environment have both an acute and chronic impact on the environment, which may be very severe and can severely diminish biodiversity and greatly reduce populations of sensitive species. Where toxic metals and organics are present, this can lead to chronic toxin accumulation in both local and far-distant populations. Rivers impacted by leachate are often yellow in appearance and often support severe overgrowths of sewage fungus. The contemporary research in the field of assessment techniques and remedial technology of environmental issues originating from landfill leachate has been reviewed in an article published in Critical Reviews in Environmental Science and Technology Journal. Problems and failures with collection systems. Leachate collection systems can experience many problems, including clogging with mud or silt. Bioclogging can be exacerbated by the growth of microorganisms in the conduit. The conditions in leachate collection systems are ideal for microorganisms to multiply. Chemical reactions in the leachate may also cause clogging through generation of solid residues. The chemical composition of leachate can weaken pipe walls, which may then fail. Landfill leachate contains a large amount of organic matter and ammoniacal nitrogen. As such, it has become a complex and difficult issue within the water treatment industry. The activated sludge process has been found to be a good solution with low processing costs and is now therefore the core process for leachate treatment, especially for nitrogen removal. Treatment of leachate using the activated sludge process includes the removal of organic matter, ammoniacal nitrogen, and total nitrogen (TN). The core method for the removal of organic matter involves anaerobic treatment supplemented with an aerobic process. Ammoniacal nitrogen is commonly removed using the conventional aerobic treatment, and advanced TN removal is achieved using endogenous denitrification or an anaerobic ammonium oxidation (ANAMOX) process. Since biological processes are the most economical method for TN removal, a key issue is how to tap the full potential of the activated sludge process and improve TN removal from leachate. Treating landfill leachate. Since leachate contains large amounts of organic matter and ammoniacal nitrogen, general disposal methods have included physical and chemical pretreatment followed by aerobic and anaerobic biochemical processes, concluding with further physical and chemical methods for final in-depth treatment. The main functions of pretreatment are to remove suspended solids, degrade some of the organic matter and ammoniacal nitrogen, reduce toxicity, and improve the overall biodegradability of the leachate. This is achieved through coagulating and stripping the ammoniacal nitrogen from the leachate. In physicochemical treatment, the separation of suspended particles from the liquid phase is usually accomplished by coagulation, flocculation and sedimentation. Coagulation, flocculation processes have been widely used as alternative treatment to remove leachate pollutants such as BOD, cod, TSS, heavy metals, color, and nitrogen compounds prior to other treatment methods. It is often coupled with treatment methods like biological process, chemical oxidation, adsorption or filtration to achieve desirable effluent quality. In spite of being economically, the dewatering and disposal of the precipitated sludge could be laborious and time-consuming. In this manuscript, brief discussions on coagulant and coagulant's aid in landfill leachate treatment is discussed with respect to their mechanism. Coagulation is generally defined as destabilization of a colloidal suspension or solution. On the other hand, flocculation is the process whereby the destabilized particles are propagated to gather and agglomerate into larger flocks. Although coagulation and flocculation are two distinct processes, they have been used interchangeably due to the confusion resulted from water treatment industry itself. The same goes for the terms coagulant and flocculant. However, it is pertinent to assert that coagulant is often used to describe any substances that can induce both coagulation and flocculation. Despite having recent advancement of landfill leachate treatment technology, it is well perceived that coagulation and flocculation is still predominant for the treatment of landfill leachate is widely practiced by the many landfill operator. Accordingly, it is assumed that prehydrolyzed coagulants such as PACL, PFCL, PFS and PFCL can be considered as the superior coagulants due to better color removal and high pH affinity towards leachate. In fact, ferrous sulfate can also be considered as a better coagulant over other metallic salts. Having said that, the emerging of starch-based coagulants in leachate treatment is seen as promising approach which can reduce dependence of pure coagulant which can effectively improve sludge production during flocculation process. However, until now, the applicability of the discussed coagulants are yet to be documented and extensively discussed. Further studies required to evaluate their application for landfill leachate treatment with respect to broad range of its parameters that need to be observed in following to Department of Environment permissible discharge limit. The function of the subsequent biochemical stage is to remove the biodegradable organic matter and ammoniacal nitrogen. The core technologies in these biochemical processes are, for example, the upflow anaerobic sludge blanket UASB membrane bioreactors MBR, the anoxic-oxidase/O process, and sequencing batch reactors SBR. The later deep treatment of leachate further removes organic matter and TN and can include Fenton oxidation, electrochemical processes, activated carbon adsorption, and membrane treatment processes. This largely biochemical disposal method results in most biodegradable organic compounds and ammoniacal nitrogen being removed, along with a portion of TN. However, the leachate water still contains a large amount of refractory organic compounds and some TN. In order to achieve current discharge standards, Double membranes using nanofiltration and reverse osmosis are employed as safeguards. The removal of organic matter by activated sludge leachate contains a considerable amount of both biodegradable and non-biodegradable organic matters. Activated sludge processes can effectively remove biodegradable organic material by completely converting it to carbon dioxide and water. The process can involve anaerobically or aerobically activated sludge. The advantages of an anaerobic process are that it has low energy consumption and can produce energy itself. The disadvantages are that fluent cod is high and retains some biodegradable organic matter. Alternatively, the advantages of an aerobic process are high biodegradation and organic removal rate, as well as good water quality. A disadvantage is high energy consumption throughout the process. Anaerobic activated sludge process. The anaerobic activated sludge process for treating landfill leachate can include upflow anaerobic sludge blanket UASB, anaerobic membrane bioreactor MBR, and expanded granular sludge blanket reactor EGSB. The UASB process results in high removal efficiency and large volumetric loading. This method is therefore often used to treat leachate with high organic content. Anaerobic MBR contain a high concentration of sludge and the effluent quality from this process is good. The EGSB, a third-generation anaerobic reactor, has the characteristic of high volumetric loading. Aerobic activated sludge process. The aerobic activated sludge process for treating leachate includes sequencing batch reactors (SBR), aerobic membrane bioreactors (MBR), the A/O process, and biofilm reactors. SBR are the predominant technology used in landfill leachate treatment because of their simple structure and large capacity. MBR are often used to treat leachate because of their high sludge concentration and good effluent water quality. The A/O process is often used to treat leachate because of its strong nitrogen removal. The rate of cod reduction is also very good when A/O is used to process landfill leachate. At present, the aerobic activated sludge process is used to remove ammonium from leachate. However, the efficacy of cod reduction is also very important. Once aerobic treatment of leachate is complete, biological organisms can be almost completely removed. Consequently, threats to the environment caused by landfill leachate are significantly reduced. The removal of organic matter by an activated sludge process is considered the most effective and economical way of achieving the desired outcome. The low energy consumption of the anaerobic process combined with the efficiency of the aerobic method could greatly reduce the environmental harm caused by leachate. However, due to the complex composition of leachate, large amounts of organic matter remain in the final effluent discharged after these biological treatments, and this makes it difficult to reach regulatory standards. Further development and more effective disposal methods are yet required. The removal of ammoniacal nitrogen by activated sludge. Ammoniacal nitrogen found in leachate typically exceeds 1,000 mg/liters, although some leachates contain even higher levels of up to 3,000 mg/liters. Significant discharge of ammoniacal nitrogen directly into the surroundings can cause great harm to the environment and especially local groundwater systems. Many developed countries have devised strict emission standards in regard to landfill leachate. As a result, the cost-effective removal of ammoniacal nitrogen from landfill leachate has been a significant challenge for the water treatment industry. Accordingly, activated sludge processes have been key methods in ammoniacal nitrogen disposal because of the low associated costs and low secondary pollution. Ammoniacal nitrogen removal by SBR are the preferred process used for landfill leachate ammoniacal nitrogen disposal. Granular sludge sequencing batch reactors (GSBR) provide a new process with high rates of nitrogen removal. Ammoniacal nitrogen removal by MBR Kanzani et al. Used an MBR to dispose of leachate which averaged cod and ammoniacal nitrogen levels at 63-61 mg/L and 1497 mg/L, respectively. Ammoniacal nitrogen was removed at a rate of 95% and a stable shortcut nitrification rate of 90% was achieved. Olthagari et al. Used a sequencing batch MBR in their study. Cod in the leachate was 1550 mg/L to 1122 mg/L and ammoniacal nitrogen was 288 mg/L 434 mg/L. The results showed that the cod and ammoniacal nitrogen removal rates in summer were 63.4% and 98.2%, respectively. The cod and ammoniacal nitrogen removal rates in the winter were 53.2% and 99.2%, respectively. Zhang et al. Used a combination of NMBR with N oxidation and reverse osmosis to process leachate. Cod of the MBR influent was around 1500 mg/L, and the ammoniacal nitrogen level was between 600 mg/L and 700 mg/L. The cod removal rate of MBR was more than 95% and the ammoniacal nitrogen removal rate was more than 80%. Additionally, Remes et al. Studied MBR leachate treatment, observing an average cod level of 1600 mg/L and an average ammoniacal nitrogen level at 600 mg/L. In order to ensure the success of the tests, the researchers used diluted leachate at the beginning of the study. When the process was considered stable, the proportion of leachate was gradually increased until the influent was composed entirely of leachate. The rates of reduction in cod and ammoniacal nitrogen were more than 50% and 95%, respectively, when ammoniacal nitrogen levels were below 600 mg/L. When ammoniacal nitrogen in the influent was above 800 mg/L, the removal rate clearly declined, indicating that high ammoniacal nitrogen levels impact the stability of the system. After denitrification through the addition of carbon, the TN removal rate was 80 to 90%. Other processes to remove ammoniacal nitrogen. There are many activated sludge methods used to dispose of leachate in addition to SBR and MBR. These include the conventional continuous flow and A/O processes, the use of rotating biological contactors (RBC) and sequencing batch biofilter granular reactors (SBGR), as well as combinations of activated sludge processes. The continuous flow process has a simple construction and high rate of ammoniacal nitrogen removal. Because the A/O process has both nitrification and denitrification applications, it can remove not only ammoniacal nitrogen but also TN by using a reflux nitrification liquid. Chen et al. Modify the A/O process to process the leachate in their study. An anoxic tank was added after the aerobic tank for denitrification. RBC is easily managed and has low consumption. The SDDGR is a new type of activated sludge process which is characterized by a high concentration of sludge and effective leachate treatment. Because of the large amount of contaminants in leachate and their complex components, some studies use a combination of processes to ensure the effectiveness of the treatment. For example, Liu et al. Studied the two-stage A/O and MBR process to treat leachate. The MBR replaced the secondary sedimentation tank in the standard A/O process. This ensures not only that the sludge concentration of the system is maintained but also that the removal of cod and ammoniacal nitrogen is optimized. Since ammoniacal nitrogen has strong chemical stability, it is very difficult to remove it through standard physical or chemical methods. Activated sludge processes are therefore the main technologies used for the removal of ammoniacal nitrogen today. Whichever process is used, most ammoniacal nitrogen found in leachate can be effectively removed through acclimated nitrification of or nitrifying bacteria. Because high levels of ammonia nitrogen have high toxicity, in an actual application, the influent ammonia nitrogen load is very important to understand and control. A high ammonia nitrogen load may poison microbes and reduce the removal rate of the system. Conventional activated sludge processes might achieve the ammoniacal nitrogen emission standards for landfill leachate. However, leachate organic matter is depleted during the nitrification process, which poses significant challenges for traditional denitrification processes. In order to solve the problem of TN removal, a number of researchers identified that adding the further carbon source could initiate advanced denitrification. However, the cost of this approach was considered too high and not applicable in engineering scenarios. In order to reduce processing costs for TN removal, researchers have used more advanced treatment processes in recent years, such as endogenous denitrification and the anaerobic ammonium oxidation process (ANAMMOX). These processes can not only meet the requirements of leachate TN removal but also have low associated costs. This is of great significance to meet the needs of the industry and to promote further development of landfill leachate treatments. TN removal by endogenous denitrification. Denitrifying bacteria are able to maintain the carbon source during leachate treatment. When sewage has no external source of carbon on which it might draw, this kind of bacteria uses internal carbon sources from within itself for denitrification. If this characteristic could be successfully enhanced, advanced denitrification could be achieved for landfill leachate without the addition of an external carbon source. In conclusion, advanced nitrogen removal can be achieved through endogenous denitrification. The disadvantage of this process is that it can only treat early and medium-term leachates with a C/N ratio that is greater than 4. If the C/N ratio is below 4, the technology cannot be used. TN removal by anaerobic ammonium oxidation (ANAMMOX) is an advanced autotrophic denitrification process. Its biggest advantages are that it requires no carbon source and that TN removal efficiency is high. The main difficulty related to this process is the source of nitrite. The ANAMMOX currently used for treating landfill leachate has two major categories: one-stage ANAMMOX and two-stage ANAMMOX. One-stage ANAMMOX achieves autotrophic denitrification in one reactor. Having a small number of reactors is an advantage, but control is difficult. Two-stage ANAMMOX, which involves short nitrification and anaerobic ammonium oxidation, is performed in two reactors with two functions. The first reactor realizes semi-short-cut nitrification and the second reactor enables ANAMMOX itself. Shortcut nitrification occurs in the first reactor and the effluent is mixed with raw water to become the influent of the ANAMMOX reactor. The advantage of two-stage ANAMMOX is that bacteria are highly enriched, enabling higher nitrogen removal efficiency. Its complexity is its disadvantage. Shortcut nitrification by activated sludge SBR are especially conducive to realizing shortcut nitrification in landfill leachate. Thus, there are two ways to realize shortcut nitrification: adjust the alkalinity of the leachate or the pH level of the effluent. Due to significant differences in water quality of leachate, it is difficult to maintain stable shortcut nitrification by only controlling the pH and alkalinity of the leachate. How to realize stable shortcut nitrification requires further exploration and innovation. One-stage and two-stage ANAMMOX dissolved oxygen is very important in one-stage ANAMMOX. Intermittent aeration could resolve disturbances from dissolved oxygen on the ANAMMOX bacteria, but manipulation is very complex. The two-stage ANAMMOX is more complicated than the one-stage version, but removal efficiency is much higher. Meow et al. Used 3 SBR in the treatment of leachate. The system included a carbon removal SBR, a shortcut nitrification SBR, and an ANAMMOX SBR. The carbon removal SBR uses simple aeration to remove organic matter and therefore ensure anaerobic ammonium oxidation activity which would be otherwise inhibited. The function of the shortcut nitrification SBR is to provide nitrite for the ANAMMOX SBR via a shortcut nitrification process, and the ANAMMOX SBR completes the process with final denitrification by ANAMMOX. Adding fillers significantly improved the efficiency of the nitrogen removal in the system. The function of the A/O process was anoxic denitrification and shortcut nitrification. The A/O effluent entered an intermediate tank and then entered the UASB along with raw water. TN removal has been a problem in all previous research and activities associated with leachate treatment. As new technologies, ED and ANAMMOX have positive and negative characteristics. The biggest advantage of ED is that no external carbon source is needed to obtain high TN removal and operation is simple. A disadvantage of this process, however, is that it can only process the leachate when it contains enough carbon, and this limits its application. ANAMMOX is a hot water treatment technology, and its advantages are low costs, high TN removal rates, and not needing an external carbon source. However, the drawbacks of ANAMMOX are that it is a complicated process and management of the system is difficult. Moreover, the ANAMMOX bacteria are difficult to obtain and slow to grow. The domestication of the system is problematic. To our knowledge, there are no studies reporting photocatalytic UV/CO2 pretreatment enhancing biodegradability of refractory organic compounds in the complex medium such as LAN-LL leachate. We are the RSD to couple the biological and photocatalytic treatments to improve the biodegradability of the LAN-LL leachates. The RSD stage of biological treatment resulted in nitrication oxidation of ammonia to nitrite and nitrate and removal of biodegradable organics from the leachate. At the end of photocatalytic treatment, a total decoloration was observed. COD and TOC significantly decreased, ensuring its low concentration, below the threshold value for direct discharge of leachate according to the legal restrictions amounting to 125 mg O2/L and 30 mg C/L. respectively. Photocatalysis brought about conversion of refractory organic from the land leachates into readily biodegradable species bog. It was proved that the bog fraction formed in that way can be removed via aerobically biological oxidation. Similarly, the organic fraction bog can be used by heterotrophies denitrate during the reduction of nitrite or nitrate to N2. However, the amount of biodegradable species provided to denitrate bacteria from photocatalytic stage will allow to meet the standard with respect to N concentration. Landfill leachate treatment and technology reduce landfill leachate volumes at brine concentrations in excess of 30% solids by mass outside reverse osmosis range. Salt macro evaporator crystallizer pilot projects completed with 4 top U.S. solid waste management companies produce fresh water to meet regulatory requirements, generate highly concentrated brine or solids for return to landfill. The salt macro evaporator crystallizer technology, built for reliability and extreme brine concentrations, multiple effect for energy efficiency, burn 1/4 the gas versus conventional leachate evaporators without the emissions, modular/portable and easy to operate, no steam tickets. Salt macro evaporator crystallizer process for effects to recycle heat of evaporation, burn 1/4 the gas. Landfill gas-fired packages available. Effects 1 to 3 closed to atmosphere, no leachate air emissions, and effect for used for cooling as a cooling tower. Effect 4 can be closed for 0 leachate air emissions. Salt macro evaporator crystallizer attributes: no membranes, no pretreatment, solves conventional evaporator crystallizer reliability problems, scaling, no evaporation on hot tubes, no boiling induced scale, non-stick/non-corrode, gel-coated fiberglass construction plugging and organics, high circulation rate, low temperature, self-cleaning maintainability, built-in automated cleaning cycles, no pressure vessels, no confined spaces, modules remove readily, spare parts stocked in Canada. Automation, intelligent self-start/stop/clean. Salt macro evaporator crystallizer pilot produced freshwater, meeting discharge limits, and solids for concentrated brine with 45 to 60% total solids, 100% reliability, 24/7 remote operations, 90-day continuous front post-treatment of high ammonia. Waters may be required. Ammonia is volatile and can be suppressed pH or post-treated. Many waste treatment facilities are located in mountain areas, and therefore, sufficient consideration to the surrounding environment is needed to keep clear streams as well as our source of water. What is required to take preventive actions against seeping water emitted from those facilities is, indeed, advanced water treatment technology that is strongly backed by science and technology. DT module system is a water treatment technology using reverse osmosis membrane which is utilized for production of ultra-pure water for seawater desalination and semiconductor. With this advanced technology, we will be able to contribute to environment protection in these areas by implementing a water treatment system that can handle leachate discharged from waste treatment facilities safely with stability. Features: simple process. Treated water is as safe as natural water, very economical, adding pressure to the raw water side. Petitioned I reverse osmosis membrane. RO membrane can make only water H2O penetrate through the RO membrane. By using this mechanism, salts and organic materials contained in raw water can be removed. This is the reverse osmosis method, RO method. In addition, the cross-flow system can prevent the membrane from contamination and clogging. Most typical leachate treatment process combines biological waste treatment, denitrification, flocculation, sedimentation, sand filtration, activated carbon adsorption, and chelating adsorption. DT module system is a very simple treatment process for that only pre-treatment and RO membrane treatment are implemented. We recommend two cost-effective and simple processes: coagulation, RO, composting coagulation, spray drying, composting wherein leachate is passed through coagulation and flocculation stage. Flocculated sludge is collected and sent for composting with aerobic microorganisms, and filtrate is then passed through reverse osmosis or spray drying process. RO-treated water is as safe as natural water, whereas RO waste is treated for composting with aerobic microorganisms. In spray drying of filtrate after coagulation, the water will be evaporated to air and spray-dried leachate will be treated with aerobic microorganisms for composting. All the above composted matter can be used for agricultural purposes. Problem statement: sanitary landfilling is the most common way to eliminate solid urban wastes. An important problem associated to landfills is the production of leachates. This study is a review of landfill leachate treatments. Approach: the advantages and disadvantages of the various existing leachate treatments discussed under the items. High leachate channeling combined treatment with domestic sewage. Recycling II biological processing aerobic and anaerobic II chemical/physical treatment flotation, coagulation/flocculation, chemical precipitation, adsorption, ammonium stripping, chemical oxidation, ion exchange and electrochemical treatment, IV membrane filtration, microfiltration, ultrafiltration, nanofiltration and reverse osmosis. Conclusion: the major fraction of old or biologically treated leachate was large recalcitrant organic molecules that are not easy removed during biological treatment. So that, in order to meet strict quality standards for direct discharge of leachate into the surface water, the development of integrated methods of treatment, the combination of biological, chemical, physical and membrane process steps, were required. Today, the use of membrane technologies, more especially reverse osmosis RO, either as a main step in a landfill leachate treatment chain or as single post-treatment step, had shown to be an indispensable means of achieving purification. Optimal leachate treatment, in order to fully reduce the negative impact on the environment, is today's challenge. But the complexity of the leachate composition makes it very difficult to formulate general recommendations. Variations in leachates, in particular their variation both over time and from site to site, means that the most appropriate treatment should be simple, universal and adaptable. The various methods presented in the previous sections offer each advantages and disadvantages with respect to certain facets of the problem. Suitable treatment strategy depends on major criteria: the leachate characteristics such as cod, bob, NH3N and age of leachate. The knowledge of these specific parameters may help to select suitable treatment processes. Table 3: the final requirements given by local discharge water standards. During many years, conventional biological treatments and classical physico-chemical methods are being considered as the most appropriate technologies for manipulation and management of high-strength effluents like landfill leachates. When treating young leachate, biological techniques can yield a reasonable treatment performance with respect to cod, NH3N and heavy metals. When treating stabilized less biodegradable leachate, physico-chemical treatments have been found to be suitable as a refining step for biologically treated leachate. in order to remove organic refractory substances. The integrated chemical, physical, biological processes, whatever the order, ameliorates the drawbacks of individual processes, contributing to a higher efficacy of the overall treatment. In the recent years, with the continuous hardening of the discharge standards in most countries and the aging of landfill sites with more and more stabilized leachates, conventional treatments, biological or physico-chemical, are not sufficient anymore to reach the level of purification needed to fully reduce the negative impact of landfill leachates on the environment. It implies that new treatment alternatives species must be proposed. Therefore, in the last 20 years, more effective treatments based on membrane technology has emerged as a viable treatment alternative to comply and pending water quality regulations in most countries. Today, membrane processes, and most particularly RO and NF, offer the best solution and have been proved to be the more efficient, adaptable and indispensable means of both achieving full purification rejection rates of 98-99% for RO and solving the growing problem of water pollution. However, landfill leachate RO feasibility is highly conditioned by the control of concentrate treatment costs and the choice of the feed pretreatment mode in order to reduce membrane fouling. Biological pretreatment are often proved ineffective as RO pretreatment. On the contrary, lime precipitation appears like a promising option for the pretreatment of RO membranes and the removal of colloidal particles and organic macromolecules that are the principal RO effluents of landfill leachates. In the same way, microfiltration and ultrafiltration have proved to be suitable, provided that they are preceded by physico-chemical process as lime precipitation. Residue production, which constitute a capital environmental concern, still remain major hurdle, since it is usually unusable and has to be discharged, further treated or landfilled. The transport to an incineration plant equipped for the burning of liquid hazardous waste remains the preferred option in spite of many controversies, but leads to high treatment costs. A very big thank you for watching and listening to our presentation.